Okay, then I hope I'm audible. Okay, so welcome back. And this is actually I'm considering this. You can consider this as a special session rather than a problem-solving session. This can be considered to be a revision session for the entire session, sort of for the entire course that we have been a part of. So this can be considered as a revision session for the course fluid mechanics and its applications. And for today's session I will basically be revising the concept that we have discussed. I will touch upon the concepts, some important parts of the course, like important concepts, so that it could help just for recapitulation, or like if you just have a time to look a watch the video, watch a 1 hour or 1.5 hour video before your final exams. So at least you can easily uh, tackle the conceptual questions in that exam. So keep with that idea in mind, we can I have considered to take this session. So I'll go upon the concepts, revise some of the basically revise revise the entire course, or as much as possible within the given time frame. And uh, if like any one of you have any doubt in between, so you can just ask and then we can discuss about it. Okay, so to start with, we discussed with the vast applicability of fluid mechanics in our day-to-day life, starting with the obvious examples such as automobiles, watercrafts, spacecrafts, sports ball dynamics, rather than uh, like and in general sports, then process and power plants. And even some examples will be like, it's for a beginner or for a layman, it's difficult to concept understand that the concept of fluid mechanics are still applicable in those areas, right? For example, in the case of human body, nuclear explosions, food and drinks, and even something that's not so fluid, like for example traffic flow, right? Right. You will eventually see like even the traffic flow or the movement of cars in a congested traffic can also be modeled by understanding the concept of fluid mechanics, or rather I must say the understanding the concept of conservation, right? Conservation laws. So uh, as a fundamental understanding or a fundamental beginning thought process, I would tell you that, like, to tackle any fluid mechanics problem, like obviously, like, not the uh, not with the understanding that you will be able to completely solve it, but if you are trying to tackle any fluid mechanics problem, then you must apply you and like if you don't have any idea like how to approach it, then then I will give you a trick. And the trick, like, I will give you a trick to solve any kind of fluid flow problem. Okay, and the trick is that you can approach such kind of problems by by imposing the concept of conservation. Okay, conservation. And by conservation I imply to mass conservation, sorry, momentum conservation, and energy conservation. Okay, and in the uh, context of fluid mechanics, like, we mostly deal with mass and momentum conservation. Okay, but it does not mean that the energy conservation has to be violated. Okay, can be violated. No, it's not like that. Energy conservation has to be taken care of, but for most of the fluid flow problems where we are not dealing with temperature changes, then the entirety of the problem can be solved or rightly approached by by imposing mass and momentum conservation. Okay, so mass will basically take care of the continuity, and momentum conservation basically will basically take care of the net forces that acts on the fluid flow system. Okay, so that's the trick. So uh, these conservation laws like play a very vital role in the very foundation of this course or this subject, and is applied repeatedly as you will eventually see, as you already saw, and will eventually see in this revision session, that how this mass and momentum conservation are repeatedly applied to understand the fluid flow problem. Okay. Then we look upon the basic specific regions of application of fluid mechanics in our modern world. So I guess we can. It's not important to go thoroughly to thoroughly to through each and every point. So that's fine, but still okay. Then we saw the fascinating. We again also discussed the fascinating behavior of fluid mechanics, of how some contradictory features of fluid mechanics, which may seem contradictory to a layman, but is in fact very much applicable in the context of fluid mechanics, or a person who has an expertise in the domain of fluid mechanics. For example, let me take the first statement. Like, rough surfaces may reduce frictional resistances against fluid flow instead of acting as hindrances. And the example is dimples in golf balls delay flow separation. Okay, and this is the example. This is the very example that we have discussed in our final session the final problem solving session, where we discussed that how the presence of dimples upon the golf ball helps in delaying the boundary layer separation over the golf balls, and thus helps in delaying the flow separation over the golf ball, and thus increasing the time of flight of the golf balls. Okay, so we discussed that. So I guess Sai joined the session. So Sai, this session is a revision session. So we are basically revising the entire course through this session. So if you have any doubt, you can ask. You can stop and ask. But basically a revision session. So we will be revising the entire subject for this today's session, and we will go like that. Okay. Or if you have any specific doubt, you can ask. That's also fine. Okay, so that's fine. Sorry. Okay, then I guess, and we can then start with our basic concept that we have discussed. So there were many terminologies that we have discussed, but the first one that we thoroughly discussed was the concept of continuum or continuum hypothesis. Okay, so it basically means that for the applicability of the governing equations that we devise for understanding fluid mechanics, that is basically the partial differential equations that we devise for modeling the fluid flows, are only applicable when the domain over which these equations are applied is continuous. Okay, and if viewed through a eyes of a layman, and considering fluid the fluid domain to be a accumulation of small fluid particles, then the concept of continuum or the continuous nature of the domain becomes a question, right? So, but again, as we saw, like, there are certain parameters that we need to consider before concluding whether the continuum hypothesis can be imposed or not. Okay, so the first term that we discussed was the concept of Knudsen number, where we saw that the Knudsen number is given to the ratio of lambda by L, where lambda signified the mean free path of the fluid particles, and L referred to the characteristic length scale of the fluid domain. Okay, so we saw that if this Knudsen number is very less than much less than 1, then the system can be considered to be densely packed, and the continuum hypothesis can be easily applied. But if the Knudsen number was greater than 1 or much greater than 1, then we saw that these such systems are considered to be very rarefied, or like the fluid particles can be considered to be very much apart from each other. So the concept of continuum is not applicable in such cases, and thus the governing equations for the fluid flows, that is the Navier-Stokes equation, fail in such kind of scenarios. Okay, so these are the conditions that are required for the applicability or the validation or the validity of the governing equations of fluid flow. Okay, then we again discuss the concept of control system and control volume. So basically the concept of system and control volume move in parallel with the concept of Lagrangian and Eulerian approach, right? The control system approach can be considered to be the Lagrangian approach, and the control volume approach can be considered to be the Eulerian approach. Okay, so and I guess we will eventually see this in the later part when we are discussing the fluid kinematics part. So if I want to introduce it, it would basically mean that if we are considering a particular fluid particle in our domain, and we are following that particle throughout the domain and understanding and seeing the changes in the various flow parameters as the particles move through domain. So such kind of approach is known as the control system approach or the Lagrangian approach. Okay, and but as it may be clearly understood that such kind of approach where we follow each and every particle in a particular fluid domain is extremely difficult. First of all, it's extremely difficult or extremely costly to be devised, and moreover is very tedious. It's more, even though if it is possible, but it's very tedious to conceptualize and apply it to our problem, right? So that's why the mathematicians or the fluid mechanics scientists have devised the approach of the Eulerian approach or the control volume approach, where we define a particular region in the domain, and then we see how the movement of flow across the domain results in the variation of flow parameters. That is basically the net forces that acts on that particular domain, and then carry on our calculation or analysis, right? So that is basically the control volume approach, okay, or the Eulerian approach. So even though this, if you look in terms of accuracy, it may happen that the control system approach or the Lagrangian approach may be very, very accurate or give you very accurate results, and in turn that's why it's also being used in different kind of problems. It's still being used for different kind of problems, but because of the cost or the tedious nature of this Lagrangian approach, researchers or basically engineers tend not to use it for their day-to-day purposes, right? And in general they tend to use the Eulerian approach, which may incur some kind of inaccuracy or some kind of errors in the calculation, but those kind of errors are completely acceptable, and in fact gives very accurate results in terms of the variation of trends of various flow properties, right? So that's why the Eulerian approach cannot be considered to be like the substitution of each other, but rather they go hand in hand. So after that we basically discussed about the shear stresses or the traction vector also, where the traction vector is basically devised to understand devised to represent the shear stresses that acts on a fluid element in a particular direction, and then that can in turn be used to define the particular the surface force in a particular coordinate axis or in a particular direction. Okay, so that's how the traction vector was defined, and then I guess we will directly jump to the concept of pressure, where we saw that where we also discussed about the Pascal's law, which stated that the net pressure force is transmitted equal in all directions. So that was the Pascal's law, and we also discussed about the concept of mechanical pressure and how it is different from the thermodynamic pressure, right? So the mechanical pressure is basically defined as the negative of the mean of the normal stresses that act on the fluid element. Okay, so we also saw that in general the mechanical pressure is equal to the thermodynamic pressure, right? So Pm is in general equal to P thermodynamics, say, right? But there are certain instances where this equation becomes invalid. So basically that instances arise when the system undergoes rapid changes like if the forcing term or the forcing scenario is such that results in rapid changes of fluid properties in the uh, flow domain, and the system is not able to cope up with this rapid change, in that scenario or in that context, this equation fails. Okay, this the validity of the equation is not acceptable anymore, so this equation becomes invalid, and which will eventually we eventually see that it is actually an outcome of the Stokes hypothesis, where or in which scenario the Stokes hypothesis becomes valid or invalid, and in that scenario only uh, this equation is valid. Like when the Stokes hypothesis is valid, like basically mu is equal to, basically the second coefficient of viscosity, that is represented by lambda, is equal to minus 2 by 3 mu, or the fluid is incompressible. And only in those scenarios this equation becomes valid. Okay, so that we will discuss when we discuss the fluid dynamics part, but still, okay. So then I guess we discussed about the concept of density, or how the continuum hypothesis is also imposed while defining the very concept of density. So I think I don't need to repeat that. It's quite simple and self-explanatory. So this diagram explains everything quite properly, so I don't think I need to revise it again. So okay, so yes, now there is an important concept, that is the concept of bulk modulus. Okay, so it's basically defined by this expression. It's basically the ratio of the change in pressure divided by the over the change in the net volumetric strain. Okay, or basically the ratio of the change in pressure to the volumetric strain. Okay, sorry if I mispronounced or misstated the definition or the terms, so I'm sorry for that. So the bulk modulus is defined as the ratio of change in pressure over the net volumetric strain. Okay, and in the context of compressible and incompressible flow, so if the incompressible flow and compressible flow, so could anyone please tell, like, what does it signify? Like, for incompressible flow, what must be the value of K? Should be very high or very low? Okay, like, it's fine. So it's a revision session, so that's fine if nobody answers, but still. So if you look from this expression itself, okay, from this expression itself, for a certain change in pressure and certain volume, if the change in the volume is very very low, so it will basically imply that the denominator is very less, so it will result in a large value of the K, which is basically the bulk modulus. So it basically means that for incompressible flow, when the net change in volume is very small, the value of bulk modulus is very high. Okay, and in the case of compressible flow, where there is a considerable change in the volume of the fluid element, there the value of bulk modulus is low compared to the case for incompressible flow. Okay, I'm not saying it's very very low, but I will say compared to incompressible flow, the value of bulk modulus is comparatively less. Okay, so that's also what I wanted to say. Sorry, let's go back. Okay, and then we also saw the concept of Mach number, where we saw that Mach number is basically the ratio of the flow velocity over the speed of sound in that particular domain. Okay, in the particular fluid. Okay, so that was the definition of Mach number, and we saw that for if the net change in density, because in the fluid flow, is less than 5%, then that kind of fluid flow can be effectively considered to be incompressible. Okay, so these are the limits where the compressible and incompressible nature of the fluid flow comes into the picture. So if you may ask, then the compressible flow can be considered itself to be a different subject completely by itself, where we'll see how the very fundamental understanding of fluid mechanics contradicts the usual observation. Okay, so not always, but there are certain scenarios where the fluid behaves in a completely different way than what it behaves in the subsonic regime. So we will see that, and this variation or this abrupt change in the behavior of the fluids is very much governed by this parameter known as the Mach number. Okay, so if Mach number is larger than 1, or basically if it is in the supersonic regime, then the fluid behaves in a different way compared to the one where the fluids are in the subsonic regime. Okay, so this change in the characteristics are governed by the Mach number of the fluid flow. Okay, so this is again important, but if you are interested, you can obviously look upon the compressible flow chapter of any standard fluid mechanics book, so you will get lots of understanding of what I'm basically trying to say. So let's just give you a clue. Like if you consider a nozzle, okay, consider a nozzle, and say the fluid is incompressible. Okay, so we saw that, like, if here this section is represented by 1 and this section is represented by 2, then if we impose the mass conservation and rho is equal to constant, basically it means that the flow is incompressible. So if rho is constant, we saw that the net volume flow rate should be constant through this nozzle. Okay, so right, basically we are applying the mass conservation. Then we also saw that it will basically imply that A1 V1 is equal to A2 V2. Okay, so if we know A2, then V2 can be evaluated as A1 V1 by A2, and since A1 is greater than A2, it basically implies that V2 is greater than V1. Okay, but this we didn't even discuss, like under what conditions or under what flow velocities is this scenario valid. Okay, so you eventually see that if you are studying compressible flow, you will see that this trend or this behavior or this nature of the fluid flow is completely reversed in the case of compressible flow. You will see that for a compressible flow, if the Mach number is greater than 1, then you will see that for the same geometry and same direction of the flow, V2 is actually less than V1. Okay, quite surprising and quite contradictory to our basic observations, but this is what happens in the high speed flow regime or high compressible flow regimes. Okay, so quite interesting. So if you are interested, you can just read it. Eventually, if there are there are various courses in NPTEL itself on compressible flow, you can also take the help of that. Okay, so I hope I was clear. So then we stumbled upon the concept of viscosity, which is again very crucial, at least in the context of subsonic flow regime, or basically for this course where we are mainly dealing or completely dealing in the subsonic regime. So viscosity by its very nature is inherent to opposite direction of the flow. Okay, so like there is a friction in the case of solids, like where the friction of the surfaces oppose the direction of motion of the object above it. Similar to that, you can understand viscosity as a friction resistance in the case of fluid flow, where it resists the motion of fluid over a particular surface. Okay, so in that scenarios where we are considering the fluid to be viscous, then the no slip boundary condition remains valid. Okay, it remains valid, which implies that the net tangential velocity above the surface would be equal to 0 at the wall. Okay, so if we consider this to be as the wall, then the net tangential velocity above net tangential velocity above this wall can be considered to be 0 in the case of viscous flows. Okay, we also saw that while we're discussing the Euler's equation, or while we're basically discussing the potential flow regime, we saw that this condition or the no slip boundary condition becomes invalid because the governing equations become singularly perturbed. The second order terms are removed because we are not considering the viscous nature of the fluid flow. So it basically implied that the sets of boundary conditions that defined that that sets of boundary conditions that were defined by the second order nature of the governing equation becomes invalid. So only one set of boundary conditions were remaining, that is basically no penetration boundary condition. Okay, in the case of potential flows. Okay, so I hope again I won't go deep, but again there was one very important crucial concept regarding non-viscous fluids and in-viscous flow. Okay, so the thing is, there is no fluid in this entire world which has viscosity is equal to 0. Okay, so if somebody tells the viscosity of the fluid can be taken to be 0, that's completely rubbish. Okay, there is no physical meaning to that statement, that viscosity of the fluid is 0. Its viscosity is a property of the fluid. So if there is a fluid, and if you are defining a fluid, there must be a certain viscosity. So we cannot tell that the viscosity of fluid is 0. But in the case of boundary layers, where we are discussing boundary layers, or the Prandtl's theory of boundary layer, we saw that there is a certain region in the fluid flow which has high viscous effects, and that particular region we termed as the boundary layer, which is exactly being defined in this particular diagram. Okay, so we told that there is a particular region in the fluid flow where the viscous effects are considerable or large. So we can assume that all the viscous effects, or the predominant viscous effects, or the dominant viscous effects are confined in this particular region. Okay, and beyond that we can consider the flow to be inviscid. Okay, or the potential, we can consider the flow to be potential flow. Okay, why this was valid? It was valid because of the fact that the velocity gradients in that particular region was 0 or very less. Okay, it's very small, and that's why if we consider this equation, tau is equal to mu du by dy, which is basically the Newton's law of viscosity, since the viscosity is non-zero, and if is non-zero, then if the velocity gradients are almost equivalent to 0, then the shear stress because of the velocity gradients can be considered to be negligible, and that's why it will basically imply a potential flow regime. Okay, okay, then we again saw that like how low viscosity would imply, like even if there's if you consider a viscous fluid, then there can obviously be some fluids which has higher viscosity compared to others. So if there's a less viscous fluid, for same inlet velocity, it will generate a thinner boundary layer compared to a fluid which has a higher viscosity compared to it. Okay, so this is the I would say simple concept, or simple what I must say, intuitive understanding. Like it can obviously be understood by intuition, but still, like, since it's a revision session, like I am pointing this out because this might help you in answering some crucial questions. Okay, so crucial conceptual based questions. Okay, then we discussed about Newton's law of viscosity. So again, this is very important. Okay, see, sometimes the students may think that this Newton's law of viscosity is universal, but it's actually not. Okay, I'm sorry, just 1 minute. Sorry. Okay, this Newton's law of viscosity is actually a special case that has been devised for like certain type of fluids, and in general we saw that most of the fluids in our day-to-day life show this kind of behavior, like they, or I guess I'm wrong in that context, so just wait for a few minutes. Okay, I'm sorry for the delay, just a few minutes. Okay. Sorry for the delay. So, as I was discussing, that sometimes like students forget that this relation, basically the Newton's law of viscosity, this relation is not universal, but is confined to certain kind of fluids. Okay, and what is observed that these fluids, this is highly applicable in the context of engineering, because most of the fluids that we deal with in the in our engineering applications are Newtonian. Basically means that the shear stress in the fluids very linearly as a shear strain. But there are various other fluids that are also common in nature, but those kind of fluids do not uh, what to say, do not satisfy or do not follow this relation. And these kind of relations, it is basically relations between the stress and the strain, are also known as constitutive relationships. Okay, this is a very I won't say advanced term, but a specific term that is not that was not introduced initially, but let me just uh, mention it here. Okay, constitutive relationships. Okay. Basically, tau versus theta dash. How the stress varies as the varies with the shear stress varies with the shear strain. Okay. So, and one of the very common fluids that does not follow the Newton's law of viscosity, but is a non-Newtonian fluid is blood. Okay, human blood. So, like if some researchers are working upon the flow of blood in our veins and capillaries, then this model fails to be valid, right? So this models fails, and they have to devise other constitutive relationships, then substitute those relationships in the Cauchy's momentum equation, and then find the specific governing equation, which will not be the Navier-Stokes equation. Okay, as I again tell, Navier-Stokes equation is itself a specific case where the fluid that we have considered is Newtonian. Okay, and if the fluid is non-Newtonian, then the validity of Navier-Stokes equation fails. Okay, so there's also one thing that you can keep in mind. Okay, so I guess you can skip past this. Yes, again you can look in this diagram where it clearly shows how there are various type of fluids that we use in our day-to-day life, but those kind of fluids are non-Newtonian. Okay, so let's just take some examples where the most common fluid that we usually discuss is water, so that is considered to be Newtonian, right? And then there are other fluids such as dilatant fluid, for example butter and printing ink, where the trend of variation of stress with theta is not linear, right? Similarly, it can be told, similar case can be told for pseudoplastic fluids such as polymer suspensions. And finally, one more example we can consider as Bingham plastic fluid, such as toothpaste. Okay, so even though it is linear, but here it basically means that the fluid will not show any kind of would not have any shear stress up to a certain point, and after certain point only after certain point of application of shear strain only, it will have certain motion, right? As you can clearly see in the case of toothpaste, like once you apply force in the toothpaste bottle or toothpaste pack, you will see that the toothpaste does not comes out suddenly, right? Doesn't comes out uniformly. Once, like after certain what to say degree of application of force only, it will come out, right? So I'm sorry that I guess I'm not able to explain it very properly, but this is the case, right? So it's also a non-Newtonian trend, even though the trend of variation is same, but it's different from water. Okay, so there is a certain threshold for shear stress that has to be crossed for the flow to for the fluid to start moving. Okay, so this is basically is meant by Bingham plastic. Okay, so I guess we can move ahead, and then let's just say we can take this example, okay, based on the viscosity of fluid. Okay, so here, like this is basically set up for this setup is these types of flows, basically the flow between two cylinders, are considered to a specific setups for, and such kind of flows are known as Taylor-Coiled flows. Okay, basically flow between two rotating cylinders. Okay, and in this question specifically, the outer cylinder is moving with a angular velocity omega, and the inner cylinder is fixed. Okay, where the radius of the inner cylinder is r1 and the radius of the outer cylinder is r2. Okay, so let's just zoom it a bit. Okay, so and the length of the cylinders is L. Okay, and the relationship between the shear stress and the shear strain is given by this expression. Tau is equal to minus mu du by dr. Okay, so we are asked to find the expression for the net moment that is required. I'm sorry. Here, according to the diagram, the inner cylinder is moving because the outer cylinder is shown to be fixed. Okay, I'm sorry for this confusion. Okay, so in this question, we are asked to find an expression for m, basically the net moment required to rotate the inner cylinder against the resistive forces because of the viscosity of the fluid within this confinement. Okay, so we need to find the expression for the net moment required to move this inner cylinder. Okay, so we consider a particular elemental surface in this region. Okay, or a particular slice of cylinder in this region of fluid. Okay, so the lateral surface area of that particular region will be given by 2 pi rl, right, where r is the radius of the or distance of the surface from the center of the inner cylinder. Okay, then the net force on that particular elemental area is given by tau into area, or shear stress into area. That will basically be mu into du by dr into 2 pi rl. Okay, then the net moment of F with respect to this axis that passes through the center of the cylinder is given by F into R, right? So that would basically mean M would be equal to minus mu du by dr into 2 pi R square L. Okay, so since like this, now if you want to find the expression in terms of the defined parameters, like here you can tell that the solution is already there because we have expressed m in terms of we have found an expression for m, but here these are not the defined parameters of the problem, right? Du by dr is not a defined parameter of the problem, so we need to eliminate this derivative and also this r term, because r term we have defined by ourselves, right, to define a particular surface in that fluid. Okay, so what we do that, we just integrate, we convert this expression in this form and then integrate u from omega r1 to 0. Why? Because since the inner cylinder is rotating, so the angular velocity of the fluid at this point would be omega r1, given by omega r1, and the velocity of the fluid at this region would be equal to 0 because of the no slip boundary condition, right? So we integrate u from omega r1 to 0 and integrate integration for this r would be from r1 to r2, right? From r1 to r2. Then integrating this, finally we get that m is equal to 2 pi mu l omega r1 square r2 by r1. Okay, so this is one example that you can consider. So now again, I guess I will skip this expression. Then we discussed about surface tension, right? So it is basically a force that is being that is required to maintain the integrity of the particular fluid elements on the surface of the fluid against the attractive cohesive forces that tend to break its integrity. Okay, break its nature. For example, if there is a bubble in this example, then since the cohesive forces of the liquid molecules in this region is much higher than the forces between the surface of the liquid and this vapor region, then it will try to pull away the integrity of this liquid bubble and try to break it, right? But nevertheless, the molecules of the above the on the surface of this liquid maintain their shape or maintain their particular shape, right? And the forces by the virtue of which they are able to maintain their integrity or maintain their shape is known as the surface energy, and such surface energy and such kind of forces per unit length is known as surface tension. Okay, so that is what it's defined. Surface tension is net force per unit length, the force that is being required to resist this breakage of these liquid bubbles, right? And such kind of forces per unit length is defined as surface tension. Okay, which is basically being denoted as gamma. Okay, sorry, sigma, I'm sorry. Okay, then we looked upon some specific cases for the expression for excess pressure. That, for example, for the case of spherical droplet, the excess pressure expression for excess pressure was given by 2 sigma by r, where r is the radius of the bubble. Then in the case of spherical bubble, then it was excess pressure was given by 4 sigma by r. Okay, it's just twice this value. Okay, spherical bubble is the value of the excess pressure for spherical bubble is just twice the value of excess pressure for spherical droplet. Okay, and then finally we saw the application of surface tension in the case of capillary rise, where the expression for the capillary rise was given by h is equal to 2 sigma cos theta by rho g r. Okay, where r is the radius of the capillary tube. Okay, that also is in the case of in the case where the meniscus is under static equilibrium, and also the, I guess, the angle and this angle is, and the angle of this, and its contact angle is, I guess, acute. I will just cross verify. Yes, the angle the contact angle is acute. Okay, so if it is greater than 90 degree, then the expression changes, so it is given by this expression. Okay, sorry, given by this expression. Now we then discuss now we deal with discuss about fluid statics. So in fluid statics, we started with discussing the hydrostatic law. So basically given by this expression of how if the fluid is static, then how the pressure varies along the depth in the fluid. So that is given by the hydrostatic law, which is given by this expression. And then we again saw how this expression helped us to define the concept of relative pressure and gauge pressure. Atmospheric net absolute pressure and gauge pressure, where gauge pressure is basically the difference between the absolute pressure and the atmospheric pressure. Okay, so then we also discussed about different pressure measuring devices such as barometer, manometer, piezometers, and most extensively we discussed about the functioning of or the working principle of manometers, and we also saw various problems. So in that case, in the case of manometers, it's initially it may seem very complex, it may seem very difficult, but in reality it's very simple. It's basically the balance of pressure above a certain datum point. Okay, so let's consider this example. Okay, in this example, if you want to measure the pressure difference between these 2 points A and B, so and this pressure difference arises because of the incoming flow. Okay, or you can also, since you already know, then you can tell that this flow is actually generated because of the pressure difference, right? This is basically the negative pressure gradient. Like if dp by dx is negative, then there will be flow in the positive x direction, as we have discussed thoroughly time and time again in the case of while deriving the exact solution of the Navier-Stokes equation. We also discussed while discussing the boundary separation, how the presence of a negative pressure gradient resembles a favorable flow condition where there is no boundary separation, and in the case of adverse pressure gradients, where the pressure gradient is positive, it may result in flow separation in the boundary layers. Okay, so we saw that. So I am telling it because you have already covered the entire course, so this is obviously understandable, right? So We initially didn't discuss it because we are not reached up to that point, but since we have discussed, we have already completed the entire course. For revision perspective, it's now good to correlate different concepts that we discussed throughout the course. Okay, so there will certainly be a pressure difference, right? So now, because of the flow, so now to evaluate this pressure difference, what we can do is we can select a particular datum which is given by this red dotted line and these 2 points C and D. Okay, so what we can do is we can, since these 2 points lie on the same horizontal level, so the net pressure on these two points are equal. Okay, which can be understood by the hydrostatic law, right? Because these 2 points are on the same elevation level, then the pressure at these 2 points would be equal. Okay, so PC would be equal to PD, right? So now what we do is, now since we need, instead of PC and PD, we need to find a relationship between PA and PB. We bring these two pressures in our context, right? So in the case of PC, we can write PC is equal to pressure at point A plus the pressure because of this liquid column, okay, which will be given by rho of the fluid into G into Z1. Okay, so that is basically what we have written here. Now in the case of PD, or the pressure at point D, it can be written as pressure at point B, PB, plus rho density of the fluid, rho into Z2 into G, plus rho of this heavy fluid, which is in our case is taken as mercury, then rho Hg into G into Z2, sorry, into Z1 minus Z2, or that is basically taken as delta H. So this is what we have written here, right? Z2 into rho Wg plus delta H rho Hg into G. So if we just modify these expressions again, we find that the pressure difference between 2 points PA minus PB is given by this expression. Okay, so we also saw about the inclined tube manometer. I guess I can just skip this part, so it is quite understandable. Then we discuss about force on plane surfaces. Okay, so we saw how the expression for the center of pressure, basically the point at which the net buoyancy force acts in the case of submerged bodies. So here in that case, the expression for the point of application of the center of pressure is given by this expression, where Yp is equal to Yc plus Ic by Ayc, where Ic the area moment of inertia of that particular surface, and Yc is the centroid of the body, right? Yc is basically known as the centroid of the body, okay, from the surface of the fluid. Okay, and here, since this term can never be negative, because Ic can never be negative, and also A and Yc can never be negative, then that's why it clearly signifies that the point of application of the center of the buoyant force is at a greater depth than the centroid of the body. Okay, so it basically means that if this is the fluid surface and this is the point, if this is the surface, then if this is the centroid of the body, then the point of application, or basically the center of pressure, is at a greater depth compared to the centroid of the body. Okay, so this is also known as the center of pressure. Okay, so let's just take this example. Okay, let us just take this example. Say if this is a submerged body, this is a, say you can consider a rectangular shaped plane submerged in a fluid, then the net force that acts on this fluid can be given by this expression. Okay, rho G A into Hc, where A is given by B into H, and Hc, or the centroid, is basically given by A. That is basically the upper edge distance between the upper edge and the surface of the fluid, and the half of the height of the body. Okay, half of the height of the body. So see, what I wanted to say again, that Yc does not mean it is the geometrical centroid of the body, but it is actually the distance of the centroid of the body from the surface of the fluid. Okay, so that's why the additional length of A was added in this context. Okay, so HC or basically YC would be equal to A plus H by 2. Okay, now if we want to find the center of pressure, then we can apply the above relation. Then YC plus YP is equal to YC plus IC by A into YC. Just substitute the value. So YC we know is equal to A plus H by 2. IC would be equal to BH cube by 12, basically the area of moment of inertia, right, with respect to this axis. Okay, and A is given by B into H, and again YC is given by A plus H by 2. Just substitute these values, substitute the given values in this expression, then you can find the value of center of pressure. Okay, so I hope this was clear. Okay, then we talked about different examples. So again, one more crucial point was regarding force on curved surfaces. Okay, I'm sorry. So in the case of curved surfaces, if we take the example of this one as drawn here, then the net horizontal forces that acts on these curved surfaces are given by the forces that act on the projection of this curved surface on the vertical projection of the curved surfaces. Okay, it basically means that if you want to find the net horizontal force that acts on this curved surface, so we need to find the net horizontal force that acts on the projection of this curved surface. That will basically be, if you consider this one, then say this red line will basically be the vertical projection of this curved surface BC, right? So this vertical line represents the projection of this curved surface BC. So we need to find the net horizontal force that acts on this projection of this curved surface. Okay, not the curved surface itself. Again, for the net vertical forces, it's much more simpler. So the net vertical forces will be exactly be equal to the net fluid that is being supported by this curved surface. Okay, so this is again one of the crucial point that we follow before solving any problems based on the net forces acting on a curved surface. Okay, so this we have discussed. So we also discussed about the stability of floating and submerged bodies. So in the case of floating bodies, the concept of metacenter came into picture. I will just not go again to define metacenter, but if there is some crucial say 1 mark 2 mark question, then the stability determine the fact that the metacenter of the body for the stability of the body, like stability of the floating bodies, the metacenter of the body should lie above the center of gravity of the object. Okay, so this is what basically I mentioned here. See, if M is above G, basically the metacenter is above the center of gravity, then the floating body is considered to be stable. If the metacenter is below G, then the floating body is considered to be unstable. And if the metacenter coincides with the center of gravity, then the body is neutrally stable. Like it will tend to be in that particular orientation throughout the towards its motion. Okay. So and again for metacenter, we follow this expression. Basically, the metacentric height or metacenter is given by this expression. Okay. So okay, then I guess we can move forward and discuss other topics because time is limited, so we need to cover many topics. Okay, now we come into the fluid kinematics part. So again, it's very important topic where we discuss the concept of streamlines, streak lines, and path lines. Basically, the flow visualization part. We saw how the flow is visualized by the help of different imaginary as well as real lines. So in the context of imaginary, the imaginary lines in our context were the streamlines, and the real lines that in our context were the streak lines, right? So we saw how these different kinds of lines help in the visualization of the flow field, and we also saw that in the case of steady flows, the streamlines, streak lines, and path lines coincide with each other and are identical, right? So we also discussed about steady and unsteady flows and their basic definitions, so I won't go again that. Okay, So while we were discussing streamlines, so by definition, streamlines are the imaginary lines in the flow field such that the tangent to these lines at any point represent the net velocity of the fluid particle at that particular point. Okay, and at that given instant of time. Okay, these are instantaneous lines. These are not time average lines, but are instantaneous lines which change at every particular instant of visualization. Okay, and more importantly, these are imaginary lines. So in general, like if you're observing some certain lines because of the application of dye in the in a particular flow, these are not streamlines, but these are actually streak lines, right? So which is basically seen by this definition that streak line is the locus of all the fluid particles which at some prior instant of time pass through a same common point. So the famous experiment of Reynolds, where he put some particular dye to visualize the motion of the fluid particles in that particular tube, those lines were actually streak lines and not streamlines. Okay, these are not to be confused with. But like if we consider that he conducted his experiments in a very properly designed environment where there were no perturbations, no high degree of perturbations in the flow field, and the flow can where the flow can be effectively considered to be steady. In those scenarios, we can tell that both the streamlines, the streak lines, and the path lines coincide with each other, and in that context, we can say that the streak lines that we observed are same as the streamlines of the flow field. Okay, so that's the scenario. And path lines, again by its very definition, is the Lagrangian description of the flow field. Right? It basically means that we are following each and every particle of the flow field, and we see how this particle moves in the flow field with respect to time. Okay, so this is what we saw. Then we also saw the basic equation for streamline, which was given by this expression. Basically, dx by u is equal to dy by v is equal to dz by w. So this was the equation for streamline. Equation of streamline. Okay. So I guess that's fine. Then we discussed about the acceleration of fluid flow, and how the net acceleration is actually the sum of the local acceleration and the convective acceleration. In the case of fluid mechanics, the motion of particles through the flow domain can also result in its acceleration, and it's not necessary that the velocity should change only with respect to time, right? So the concept of total derivative came into picture when we were discussing the net acceleration, where the net acceleration was the sum of the local acceleration given by this expression dou u by dou t, and the convective acceleration given by this expression given by u dou u by dou x plus v dou u by dou y and w dou u by dou z. Okay, so then again saw the equivalence of the Eulerian and Lagrangian approach, but I don't think we have enough time to discuss through everything. And again, since the concept of total derivative came into picture, the total derivative was again defined as a particular mathematical operator, which was given by the complete derivative d by dt was actually the sum of the local derivative dou by dou t plus this term given by the v dot nebula, where nebula denotes the operator given by nebula is equal to dou by dou x I cap plus dou by dou y j cap plus dou by dou z k cap. Okay, this expression. Okay, but again one more key point, that this expression is in vector form, right? So this expression is valid for any Cartesian coordinate system. But if we are this expression is valid for any coordinate system. But if we are considering a Cartesian coordinate system, then this is what the expression for complete derivative is. But if you are considering different coordinate system, then the expression would change accordingly. Okay, say cylindrical coordinate system or spherical coordinate system, then the expression for v dot delta will change accordingly. Okay, basically because of the definition of the nebula operator in the case of different coordinate systems. Okay, so I will just request you to wait for a few minutes, then I'll just come back. So kindly wait. Okay, I'll just come back. Okay then, thank you so much for waiting. So, okay. So we after that we also discussed about the different kinds of deformation in fluid elements, and which were basically divided into the linear deformation and angular deformation. Where, and I guess again I will not go back to the total derivation. Where, say in the case of linear deformation, deformation along a particular axis or particular direction, say along the x-axis, was given by this expression du by dx. And similarly, if we consider the deformation along all the, if we consider the sum of the deformations along all the three coordinate axes, then this sum would in turn give us the net rate of volumetric strain. So given by this expression, dou u by dou x plus dou v by dou y plus dou w by dou z, which is in turn the sum of the net linear strain along the respective coordinate axis. And this expression can also can also be written by this form. Can also be written in this form, which basically implied the divergence of the velocity field. Okay. And in the case of compressible flows, the net volumetric strain is 0. So it basically implied that the divergence of the velocity field del dot v is equal to 0. Okay. So this was the significance of the definition of the linear strain rate. And okay. So guess you can just skip this part. It's fine. We just here discuss about different ways to derive the continuity equation of the mass conservation. So that's completely fine. Okay. So I'm sorry I'm skipping many parts, but I guess it is what it is. We need to cover most of the course, since this is basically a revision session, so I cannot dig upon each and every concept again and again. So I guess I won't say that. I will just say, for the sake of time, I won't go back each and every derivation, but I can rather speak upon the basic formulas, and then you can just apply that in your problems. Okay. So since again a new student joined, so just for your context, this is a revision session, so I'm just revising the entire course again. So basically the formulas and concepts, so you can stay if you're in for revision, but other than that we will not be solving any problems in today's session. So I hope that's fine. Okay, so the rate of shear strain, okay, in the concept of fluid mechanics, is actually a second order tensor. Okay, by second order tensor I mean that so if we were to define the shear strain rate in the case of a fluid element, then it would be a 3 cos 3 matrix. Okay, and if we are discussing in the context of Cartesian coordinate system, then it will have 9 elements. So that will be given by forgive my handwriting. So I guess I made a small mistake while writing this expression. So it would be okay, and you can see that the diagonal elements, this is again one beauty, the diagonal elements actually represent the linear strain rate along a particular direction. Okay, so these all these elements in turn have their own expressions, and this represents the linear strain rate in that between those particular axes, right? Because since we saw that we define the angular strain rate, the angular strain rate as a rate of change of angle between two line elements in the fluid flow. So it basically means that since there are 3 axes, so there would be 6 independent relations between the 6 independent relations for devising the rate of change of angle between the two line elements. Okay, so here the 6 independent elements would be given by EXY, EXZ, then EYZ, and the 3 normal 3 linear strain rate elements. Okay, so why? Because EXY and EYX are equal, and EYZ and EZY are equal, and EXZ and EZX are equal. So in general this will have only 3 independent elements. Okay, it will basically EXX, EYY, EZZ, then EZX, EYX, and EYZ. Okay, 6 independent elements. Okay, so let me just erase it out. Okay. And we saw that if you're only considering the rate of change of the angle between the two line elements in the case which are initially aligned with the x-axis and the y-axis, then the expression for that is given by EXY, right? E dot xy, or epsilon dot xy, as is noted here, epsilon xy, where epsilon dot xy is given by dou v by dou x plus dou v by dou y. Okay, and similarly we also saw how we can define the angular velocity, where the angular velocity is basically the arithmetic mean of the angular velocities of 2 line elements in the fluid element, which expression is given by this, where omega xy would be equal to half dou v by dou x minus dou v by dou y. Okay, so this expression that I wrote here is actually the index notation for all the nine elements in the tensor for the angular velocity as well as the linear angular strain rate. But for right now, for the context of this course, I don't think it's necessary to understand the index notation, but still, not to get confused with, these are the index notation for the various elements of the angular velocity tensor as well as the shear strain rate tensor. Okay, so I guess that's fine. Then again we discuss our vorticity, where vorticity is given by the curl of the velocity field. Okay, and if the flow field is irrotational, then the value of the vorticity would be equal to 0. Okay, basically del cross V equal to 0, where del is the nabla operator. Okay. So yes, and now then we are also we also discuss a very important concept, that is about stream function, where we saw that stream function is valid for a steady incompressible 2D steady incompressible 2D flow, fluid flow. Okay, so in the case of a 2D incompressible fluid flow, the mass conservation equation takes the form dou u by dou x plus dou u by dou y is equal to 0. Like any of the two, like they can be u or v or v or w or u or w. Okay, but say that w is equal to 0 in this context, then the mass conservation equation takes this form. Okay, and also since it's incompressible, then dou rho by dou t is equal to 0. Okay, so keeping that idea in mind, this is the form of the mass conservation that we have. And if here in this equation, if we substitute u is equal to dou psi by dou y and v is equal to minus dou psi by dou x, then this equation would inherently satisfy the mass conservation, and thus we can define the net flow field in terms of a single variable, which would be a function of x and y. Okay, so again I will reiterate that the existence of stream function is only valid for a 2D incompressible flow field. Okay, then we are like, let me just move ahead and say, like, after that we also discuss about potential functions. So we basically found the relationship between the stream functions and the potential functions, where we saw that they form a relation such as relation given by where if we consider u is equal to dou phi by dou y, which is also equal to dou psi by dou x, and v is equal to, I'm sorry, I just made a mistake here. So if phi is the potential function, then u is given by dou psi by dou y as well as dou phi by dou x, and also v is given by minus dou psi by dou x and dou phi by dou y, where we again saw that, and this is valid for a 2D incompressible, and one more criteria is required, that is irrotational. Okay, so if these three criteria are satisfied, then we can say that the potential function and the stream function satisfy the Cauchy-Riemann conditions, right? Let me just write it, Cauchy-Riemann conditions. I am just reiterating it because I don't think I will be able to cover the potential flow part in our present revision session, but just for you to recapitulate. And there we also saw that in the case of potential flow theory, where we discussed that the flow is 2D irrotational as well as incompressible, in that case we devised an algorithm of visualizing the flow field, where we saw that first we find the potential function. Why? Because it's quite easy to find, because the governing equations are quite simple. They are basically given by del square phi equal to 0, right? Basically Laplacian equation. And since this equation is valid, then we can easily solve for phi. Solve for phi, find the velocity fields. Can find the velocity field, and also since we already know phi, we can again find the expression for psi from this relationship, and which can again help us in visualizing the flow field, right? And why we are solving the equation for phi? Because we learned that solving solving for phi was much simpler compared to solving for the stream function. So first we solve for the potential functions, then find the stream functions from find the respective relations. Then basically find a stream function from the potential function, and then we can visualize the flow, right? Because psi was easy to visualize compared to phi, and gave much more data or information about the flow field compared to phi. Okay, so that's the context of stream functions and potential functions. So that's what it is. So I guess that's all for stream functions. Then I can skip the problems because we have discussed thoroughly many problems. So yes, again. So now we discuss the dynamics of in viscid flow, basically the Euler equations. Like we are not considering the viscous term. So basically the governing equation is reduced to the Euler's equation, and in that we saw that under certain like this is the governing equation. Okay, this is the governing equation, which is termed as the Euler's equation. Okay, which has the inertia force term, the body force term, and the pressure forces, and the viscous terms are neglected. Okay, and we again saw that if we impose certain special cases or certain special assumptions in this equation in turn then results or in turn then reduces to the Bernoulli's equation. Okay, like the Euler's equation is the most generalized form of the governing equation for in viscid flows, but if we impose some certain criteria or certain assumptions in this particular type of equation, then this equation reduces to the Bernoulli's equation, which is quite simple in its form. Okay, so we saw that. Let me just go to this section. Yes, so we saw that if we impose these four conditions, this is basically in viscid flow, steady flow, constant density, and along and consider that the 2 points that we consider are along a streamline, then the Euler's equation reduces to the Bernoulli's equation. Okay, and we are also saw that if we impose further one more condition, that if del cross V is equal to 0, this is basically the flow is irrotational, then the 2 points where we apply the Bernoulli's equation can be at any 2 points in the flow field, and did not necessarily lie on the same streamline. Okay, so this is one important conclusion. So and let's here we basically saw that the Bernoulli's equation states that the sum of the net flow energy, kinetic energy, and the potential energy between any 2 points along the same streamline in the flow field remains constant, given that the flow is steady, incompressible, and inviscid. Okay, so that's what we saw. There are again some specialized form of Bernoulli's equation, so that you can just refer from the notes that I have shared. So yeah, okay. Then we solved some problems. So as I said, I won't solve any problem for today's session. It's just a revision session, so that you can just recapitulate the various concepts that we've discussed. Lots of examples that we solved regarding Bernoulli's equation, so I guess I'll just skip that. We also discussed about siphons. So okay, for revision, let me just take this example. Like if we consider such arrangement where the end of the pipe, one end of the pipe is at the surface of the liquid of the fluid that we want to extract, and another end of the pipe is at an elevation that is lower than the elevation of the surface of the fluid, then if we apply Bernoulli's equation between points 1 and 2, okay, point 1, where point 1 lies at near the at the surface of the fluid near the inlet of the pipe, and point 2 lies at this region, say at the highest level of the pipe, that go the highest level of the pipe. Then if you apply Bernoulli's equation between these 2 points, we find that P1 by rho plus V1 square by 2G plus GZ1 will be equal to P2 by rho plus V2 square by 2 plus GZ2. Okay, and since P1 is equal to, if we consider only gauge pressure, then P1 is PATM, so that can be cancelled out. Surface velocity at the surface can be considered to be 0, so V1 is 0. That's why and V2, if we consider Vx, why you can consider, because since the area of the pipe is constant at the exit and at this point, then V2 can be considered to be V exit. Okay, so V exit is equal to root 2G is a very good approximation. Okay, it's a very good approximation. Like in the case of, we also saw that in the case of Torricelli's law, and in the case of orifice also, like we saw how V2 for certain conditions, V2 can be easily approximated as root 2GH. Okay, and just just to have an approximate idea of the pressure at this point, at this point 2, we consider V exit as root 2GH, which would be same as V2, because the area of the pipe remains constant, right? So P2 can be given by minus GH, because given as minus GH minus V exit square by 2. Okay, basically if you just take Z2 at this point, then GZ1 minus Z2 would give you minus GH, because Z2 is greater than Z1, right? So P2 by rho would basically give you minus GH minus V2 square by 2, so V exit square by 2. And since this term can never be negative, so this whole term is negative, and then H is also positive, so this is also negative. This is also negative. So it basically states that pressure at point 2 is a negative pressure compared to at point 1, because it was atmospheric pressure at point 1. So it basically tells that pressure at point 2 is a suction pressure. Okay, so this difference would create a suction effect if we create this arrangement. Okay, but again, one more thing to keep in mind, that this equation is very idealistic, is devised in a very idealistic point of view, completely disregarding the viscous effects of the fluid flow, which is like completely wrong when we're discussing real fluids. So this will certainly have the flow will certainly have some viscosity, as well as the surface of the pipe, the inner surface of the pipe may also have some certain irregularities, which again creates some higher degree of friction, which will in turn lead to a very high reduction in this suction effect. Okay, so but still, as you can see, even if the accuracy of the solution, that even if the suction pressure would be quite low compared to what is the theoretical value of suction pressure, but the trend of variation of the pressure, which basically states that even in the idealistic point of view, that there will be a suction pressure given that this kind of arrangement is devised, is similar to what we will actually see in the real case, right? So that's why the importance of Bernoulli's equation comes into picture, right? Like even if it's a very idealistic point of view for the governing equation, but still at some certain scenarios, it gives a very good approximation of the real trend of variation of the flow parameters. Okay, so then we are also discuss about various flow measuring devices. We discussed about venturimeter, pitot tube, and orifice meter, where we saw that the venturimeter and orifice meter are primarily used for the measurement of the net flow rate in that particular device, and pitot tube is used specifically to measure the flow velocity in that particular flow device. Okay, so that was the main difference on the applicability of the venturimeter, orifice meter, and the pitot tube. Okay, so I guess I won't go again in the application of venturimeter, so I guess that's fine. So I guess then you can okay, you can just stop here and just discuss about the angle of the cone angle for the venturimeter, like why this is quite low, very less in the diverging section. It's as you already know by now that this angle is kept very low so that the flow can flow separation cannot take place in these regions, because we will see that if this angle is very high, and since the flow is experiencing a adverse pressure gradient. Why? Because see, since the flow this is a diverging section, and since we are basically still dealing with subsonic regime, then it will basically mean that the velocity at this point is lower than velocity at this point, at this throat region. Then since the velocity is low, the pressure at the exit will be higher compared to what pressure is here at the exit of the throat, right, of this throat section. Then it basically means that since pressure is high at the exit, it basically implies there is an adverse pressure gradient. But we also saw that adverse pressure gradient does not necessarily mean that the flow separation would take place. There are certain values of adverse pressure gradient, like it has to be sufficiently negative so that it could result in flow separation while we are discussing boundary layer flow separation, right? So keeping that idea in mind, now if this angle is made very high, that if the cone angle is made very high at the exit, then what would happen is that since there's already a adverse pressure gradient, the flow will tend to separate very easily compared to the scenario when the cone angle is kept small, right? So if there is flow separation at the exit region, it will basically imply energy losses, which we usually don't want while conducting fluid flow experiments in the case of wind tunnels. Because why I'm saying this, because wind tunnels are also made in similar shape, but also like if you are measuring if you are if you are transferring fluid from one region to another, and then we don't want a loss in the energy because of the flow measuring devices that we have fitted to measure the net flow rate in that particular pipe, right? So if the cone angle is very large, it will incur large amount of losses because of flow separation, right? And thus, in order to avoid that, this cone angle is kept as small as possible so that we can avoid this flow separation because of this adverse pressure gradient. See, the adverse pressure gradient will still be there, but the flow separation can be dealt with if this cone angle is made as small as possible, and the standard values vary from 5 degree to 6 degree. Okay. So I guess that's all. Then we discuss orifice meter. So I guess I'll skip that. And okay. So as I was just mentioning that in the case of orifice also, the exit velocity can be given by root 2gh, and thus it's a very good approximation for velocities in the case of the exit velocity in the case of siphon, right? It's not exactly same, but it's a very good approximation. Okay, that's what I wanted to emphasize. I guess then I will just skip and yes, now I guess this would be the last part for today's revision, basically integral forms of the governing equations. And here we discussed about RTT, or basically the Reynolds transport theorem, and we saw that how important this theorem or this transformation is, because see, here we saw that most of the conservation equation, that is basically the mass conservation, momentum conservation, or the energy conservation, are devised for a control system, a definite system, right? A definite system that is a particular mass, where the identity of the system or the identity of the molecules within the system remain the same. It is basically the control system approach. So all the governing equations that were devised were initially devised for a control system approach. But since we, in the context of fluid mechanics, we want to deal such kind of problems from the Eulerian point of view, that's why we needed a mathematical transformation to convert these classical equations that were initially devised in the context of control systems, and we want to have a transformation so that we can transform these classical equations in a control volume form. Okay, so that's why the RTT was devised, and we saw that the general form of RTT is given by this equation. Okay, this equation where capital N denotes the parameter or the fluid parameter that you want to conserve. That can be mass, momentum, or energy, and small n denotes the intensive value of that particular property. Basically, it means that the value of the property per unit mass. Okay, so in the case of mass conservation, this capital N would be equal to m, and small n would be equal to this n by m. That will basically imply small n is equal to 1. And then we saw that since mass can neither be created nor be destroyed by its very definition, then that's why this rate of change of mass is equal to 0 in the case of the control system approach, and thus the net mass conservation equation in the Eulerian context is given by this expression. Okay, where dou by dou t of volume integral of rho dV plus surface integral of rho Vr dot n cap dA is equal to 0. This is a mass conservation in the Eulerian perspective. Okay, and here Vr is actually the velocity of the fluid with respect to the control volume. So the control volume may be moving and may be deformable, but if we and that's why, since if the control volume is moving, then Vr would imply the velocity of the fluid with respect to the control volume. Okay, so that's what it is here. So then again we applied this mass conservation for various problems, so I guess I won't go back again, but again then we saw some certain simplifications, right? That if we consider a non-deformable control volume, then volume is not a function of time, so we can take the integral within the we can take the derivative within the integral, basically by applying the Leibniz rule, but that I have not shown here. And again, if we consider a stationary control volume, okay, then it would basically imply that Vr equal to V, right? If the control volume is stationary, then relative velocity of the fluid would be equal to the absolute velocity of the fluid, right? Then in this form of equation, okay, not in the general form, but after imposing these two assumptions, we applied Gauss divergence theorem to convert this integral form of Gaussian equation to a differential form that is given by this expression that we initially derived in the previous sessions, in the previous part of this today's revision session, right? This is basically the mass conservation equation in differential form. Okay. Similarly, after that we also saw the conservation of linear momentum, where the capital N in that context would be equal to mv, and small n would basically be equal to v, because mv by v would be equal to v. Mv by v divided by m would give us v, so small n would be equal to v. Okay, that is basically shown here. So just substitute n is equal to mv and small n is equal to v, so we get this expression, right? And here the right hand side, sorry, the left hand side or the control system part basically denotes the net force that acts on the body. Okay, and this net force that acts on the body can comprise of both surface forces and body forces, right? So we saw certain examples of surface forces as well as body forces, where we saw that surface forces basically comprised of the pressure forces, and the various kind of viscous stresses in the case of fluid flows, and body forces comprised of the forces such as the forces due to acceleration due to gravity or electrostatic forces, right? So these are various distinctions between the surface and the body forces. And then, like, once you modify or once you substitute the form of the surface and body forces in that particular equation, we finally arrived and impose the condition that the fluid that you are dealing with is a Newtonian fluid. Then we finally arrive to the Navier-Stokes equation. Okay, I guess we will eventually see here. I'm just skipping past the examples that we already dealt with. So just go through it. also discussed angular momentum, so I guess for the sake of time I will skip that part. Yeah. As I was mentioning, like if you substitute the form of the body force and the surface forces in the expression for the expression that we initially derived after imposing the RTT in the momentum conservation, then we arrive in this form of the equation. Okay, and here, like, not to be confused with, these are basically index notation that we have used to that we have used to define the momentum conservation equation, which is also known as the Navier's equation or the Cauchy's momentum equation. Okay, and here only, as I was mentioning, if we represent this shear stress in terms of the shear strain rate in by applying the Newton's law of viscosity, like if we substitute here tau ij is equal to 2 mu Eij, then this equation reduces to the Navier-Stokes equation. Okay, and accordingly, if we want to substitute different constitutive relationship for stresses, say tau ij is equal to mu Eij to the power some certain exponential power, then the equation is different equation. It's not a Navier-Stokes equation, but actually the Cauchy's momentum equation. Okay, so this equation, the Navier-Stokes equation, is actually a special form of the Cauchy's momentum equation. Okay, so I guess I will just skip this part. So let's just reach the final form of the equation and then see how much we can cover. And then yes, so in that equation, if we saw that if we substitute the this relation, that tau ij is equal to 2 mu Eij, then we arrive to the Navier-Stokes equation. Okay, here if we consider that the fluid is incompressible, okay, then basically this term would go out. This term basically implies nebula dot v equal to 0. Okay, basically divergence of velocity field is 0. I'm sorry, this term basically implies divergence of velocity field. So if we say that the fluid is incompressible, then this form of the Navier-Stokes equation reduces to this final is that right here? Okay, so reduces to this final form. Okay, which we usually solve for most of our fluid flow problems that we dealt with in our course, in this course. Okay, so now I guess I can directly go to the boundary layer theory. So we discuss the exact solutions, so I guess it's fine. Since we are limited in time, I will just review the boundary layer equations and the scaling part, and then we can just wrap up with today's revision session. Okay, so there are various things that are important part that I'm skipping. Basically the Darcy's friction factor and the Fanning friction factor and the relationship, this relationship basically. The Darcy friction factor is 4 times the Fanning friction factor, and why a relationship exists between the Fanning friction factor and the Darcy friction factor. So that I am skipping for the sake of saving time, and I will just okay. Then let's just directly deal with the boundary layer theory. So here we saw how the boundary theory was developed by Prandtl in order to overcome the D'Alembert's paradox, which stated that the net drag force in the case of a bluff body is equal to 0, but which is actually not true, because in the case of bluff bodies, the net drag force is actually the order of 1 compared to the lift forces. So that was contradictory to what was actually observed in the real scenario. So to overcome this paradox, known as the D'Alembert's paradox, the boundary layer theory was devised, which stated that most of the viscous effects in the case of high Reynolds number flow were confined to a very thin layer attached to the surface of the body, where this thin layer is known as the boundary layer, and in this boundary layer the velocity gradients are considerably high, and uh, and the thickness of this boundary layer is given by this expression where basically is defined by the point in the flow field where the velocity of the flow is 99% of the incoming velocity or incoming free stream velocity. Okay, so this is basically del y, sorry, u at y equal to del would be equal to 0.99 of u infinity. Okay, this is the definition of boundary layer thickness. So to derive the boundary layer equations, we consider the flow to be we consider a 2D form of the Gurney equation sorry, assuming that the net variation along the z direction is very much negligible, assuming that the depth along the z direction is very very high compared to the boundary layer thickness. So keeping that idea in mind, we solved the 2D form of the Navier-Stokes equation. Then we imposed a particular scaling to these terms. So I guess again I again had to skip the scaling part. This is basically comprised of the Buckingham Pi theorem and the scale factor analysis. So I'm skipping that part, but here we scaled the various flow parameters with respect to the various characteristic scales. So in the case of y-axis, we scaled y-axis as the boundary layer thickness, right? So if we scale from the continuity equation, we concluded that the free stream velocity along the y direction is given by this relation, u infinity delta by L, which can easily from which we can easily tell that the magnitude of the free stream velocity along the y direction is much lower than the free stream velocity along the x direction. Why? Because delta is much less than L. Okay, we again saw that this relation is an outcome for the fact that Reynolds number is much higher than 1, okay, which we eventually saw. So again we scaled the respective momentum equations along the y direction and the x direction, from where we saw that the y direction, the scaling of the momentum equation along the y direction gave us the conclusion that the net pressure variation along the y direction is almost equal to 0. So basically within the boundary layer, pressure is only a function of x. Okay, that is what we basically got. So after scaling the x momentum equation, if the final momentum equation that we got was given by this expression, that dou u by dou x plus v dou u by dou y is equal to minus 1 by rho dou p infinity by dou x plus nu dou square u by dou y square, where this expression is an implication of the y momentum equation. Okay, so we again saw like this, if this is general from the boundary layer equation. Okay, now here if we impose the case of flow over a flat plate where the incoming free stream velocity is the the incoming free stream velocity is actually a constant and does not vary with x, then this term was cancelled out, right? So the final equation that was left with us was of this form. The final form of the momentum equation or the x momentum equation was given by this: u dou u by dou x plus v dou u by dou y is equal to nu dou square u by dou y square. Okay, so after that we derived various expression for the skin friction coefficient, then the boundary layer thickness. We also saw how the Blasius solution helped in giving an analytical solution to the boundary layer thickness, where the Gurney equation that we eventually found for the Blasius solution was a third order non-linear PDE. So from that, after solving that equation, the relation that we got was given by this form, right? And obviously to solve these momentum equations using the Blasius solution, we took the help of the similarity solution. Okay, then we found that the Blasius solution gave us the solution that the boundary layer thickness varied in this varied as 5 varied as the negative. Let me just say it like del by x varied as rex to the power minus 1 by 2. Okay, so there's the trend of variation of the boundary layer thickness along the x direction. So this is what this is the conclusion that we got from the Blas's solution. Then using the same relations, we found the expression for skin friction coefficient. And then finally we discussed about momentum integral methods for boundary layer analysis, where we initially guessed a particular form of the velocity profile and then substitute it in the von Karman equation to find the shear stress acting on that particular surface, right? So that's what we saw. So the von Karman equation was given by, let me just go there, was given by this expression, where to find the net shear stress acting on the wall, we initially guess a velocity profile which is usually of the order of which is usually a third degree polynomial with respect to the velocity. So substitute that expression, and obviously that third degree polynomial or third degree velocity profile would have to be imposed with appropriate boundary conditions. And once we substitute the this velocity profile in this expression, then we can find the expression for the shear stress, right? So this is what the main concept behind the von Karman momentum integral equation. So this is what we have discussed. So this is what I meant with a third degree velocity profile. So you can consider a velocity profile of this form, which would have four constants a0, a1, a2, a3. Impose the required boundary conditions, which must imply to a certain physical condition, and then find these coefficients. Basically, then get the velocity profile that you have initially guessed. Substitute this velocity profile in this expression to find the net shear stress. Okay. So I guess that's all from my side. I guess that's all would be from my side for this course, and for this session, which we consider to be as a revision session for this fluid mechanics and its application course. So again, I hope that I really hope that you attended or at least watched all the problem solving sessions till now, so that I don't think this revision session would be quite very useful for you. But if you just missed some of the lectures and just want to recapitulate the entire course by the help of a 2-hour long video, then you can obviously take the help of this video. Okay, I hope that I was able to clarify some conceptual doubts, if at all it were there. And just again, like, if there's any doubt, you can just put those doubts in the discussion forum, and I will just go through that. Okay. So okay, then thank you from my side, and all the best for your exams. Okay, thank you.